Good morning, everyone. So this is the video class for the gravitation module 3, or sorry, chapter 3 for the mini course 1. The slides, you can find them in Canvas, right here. I think I would like you guys to start with that video I'm pointing at right now, because this video has a lot of information and summarizes very well what the objectives of this chapter are, which is to understand the idea behind gravity, the history of the development of the theory, law actually called, right? The universal law of gravitation, and also to understand the different models that were introduced for the solar system. Because at the end of the day, the objective of this chapter is to realize, is to understand and realize that there were a lot of changes since the moment that the Greeks were able to spot these wanderers, right? The planets, right? And they noticed that there were some particular positions and motion, in particular with Mars, that we are going to talk about today. So what you see there is obviously what happens in the absence of gravity, right? As you go farther from the Earth, the value of gravity gets smaller. Now there is an equation for it. That's not going to be evaluated, but you should know that if you know the mass of a planet, a body, a star, a moon, right? And you know the size of it, you know the diameter, then you can pretty much estimate using Newton's equation, Newton's laws. In any case, you have to remember that the ancient astronomers, we're talking about the Greeks there, right? They invented a geocentric model to explain planetary motion. What do I mean by that? Or what do they mean by that? They had the sun at the center, sorry, the Earth at the center, and every other planet, including the sun, going around the Earth, because there was this whole idea of the Earth, the sun, the Earth at the center of everything, right? And obviously, that's something that was not just elaborated, but not just taken by the church, but it was also a good way for them to put humans as the center of everything, right? Because they had this idea of the creation of the universe and all that. Nowadays, we know that that's not correct. Nowadays, we know that the planets orbit the sun, but there was a long time for that idea to be changed, because even some astronomers with quite some knowledge, they try to defend this idea with their own observations. It wasn't until Copernicus and then Galileo, Kepler, and obviously then Newton that they discovered that it was actually not the Earth at the center of everything, but the sun. So there is a model for the geocentric, right? There's a geocentric model there. So by looking at the stars that were in a fixed position, they try to explain that the other wanderers, the planets like Mars, or in the case of the moons, the moon, or even the sun, right, rising and setting, they try to explain all those ideas by the fact that everything was rotating around the Earth. That's why we see some of those objects moving in the night sky. And there's a good merry-go-round analogy there. But there is a problem though. There is a lab, the Mars lab, that you will do later this semester, where you will see how the path of Mars changes as it goes to the east, but all of a sudden, between May, June, and August, you see Mars going backwards towards the west, and then goes back towards the east. We call that the retrograde motion. The geocentric model was not able to explain that, all right? Because they consider everything going at the same speed in circular orbits, and well, there was no way that you would see Mars going to the east and then to the west and then back to the east. So there was something wrong with the model, right? So who kind of tried to fix it? Totally me, with including epicycles. What is the idea of an epicycle? Is the idea that a planet, like you see there, is rotating around somehow an empty area, and at the same time it's rotating, it's doing this, right? So let's stop the camera so you can see what I'm doing. So basically it's doing this, right? So there are two things that we know that are wrong with that model. First of all, it's way too complicated, and something we have learned in physics and astronomy, in every science actually, is that the more complicated you're trying to make a theory to fit the data, the more wrong you probably are, you most likely are. And that is generally true. And with this particular case, it was true. Now we know it. And what was the main reason that we know nowadays? Nothing can rotate around emptiness. There has to be an object there for a planet or a star or whatever, a moon, to rotate around. Because now we know more how gravity works thanks to Albert Einstein, right? Newton introduced the idea of forces, but then it was Einstein who introduced the idea of warping space and time, which is why objects go around other objects. But in any case, we're going ahead too much. Epicycles was what Ptolemy, a Greek, you know, he is known by his theorem with the trapezius. So one of the precursors of geometry, but they fixed this. And for many hundreds of years, that was the accepted idea until we had the concepts of, so that's the explanation there, so you can read it, right? So obviously they were able to explain the retrograde motion by having this, right? As the planet goes in one direction and another direction, you will see the motion of the planet going eastward and then westward. But again, way too complicated, and we know now that doesn't make any sense. They were just trying to fit the data or the observations with a model that kept the Earth at the center of everything, right? However, it was Nicholas Copernicus, the one who introduced the first glimpse, not the first heliocentric, but the first glimpse of an accepted heliocentric model. He said, well, what if we make these things more simple? And we put, so that's Copernicus there, the sun at the center. And then we have the other planets going around the sun. If that's the case, then you can actually explain very well the retrograde motion of Mars. When you guys do this lab, you will see it live. And it's very, very interesting what you can actually observe. You can see the timeline of this retrograde motion, right? And by the way, Mars is not the only one. And this is the thing about Copernicus. His only mistake was that he kept everything circular. The most symmetrical shape in the universe is a circle. So there is a problem though. If you guys have the sun, and then Mercury, Venus, and then the Earth, and you say that they're all circular, it's good, but the retrograde motion of Mars cannot be explained by that. Because you're assuming that Mars is also circular, right? There. And if you're in circular orbits, they have, even though they are closer to the sun, it's hard to explain why the Earth will go faster than Mars. At least observation-wise, it's difficult. I mean, we know that the closer you are, the faster you will move, but that wasn't very obvious back then. And the fact that they kept everything in circles didn't also help. But that's a heliocentric model there, introduced by Copernicus. So what was the way to fix this? And if you guys have watched the video, you will know who was the one who got the last answer for this. But let's keep going. So now we know that thanks to the heliocentric model, we can actually get a few more pieces of information, like the fact that the inferior planets like Mercury, Venus, they have an inferior and superior conjunction. You guys, I'm pretty sure are gonna be working on lab 3, right? And if you have already worked on lab 3 of orbits, you will have seen this, where you have to align the Earth with a planet that is closer to the sun and the sun itself to find the inferior, and then when it's farther from the Earth, the superior conjunction. That happens for Mercury and for Venus. When a planet is farther from the Earth, that's when you find the opposition and conjunction only, no superior or inferior. And that's the nice thing. For Mars, we see the opposition and conjunction, right? And that happens because there is a point where Mars is very far from the Earth. So let me show you what I mean here on the board. So there is a point where the Earth will be here, and Mars will be here. So they are not going at the same speed, obviously, right? This is conjunction here. If Mars, or when Mars is here, that's when we actually like to send missions to Mars, because it's the closest distance between the Earth and Mars. That's opposition. Align with the sun. That normally happens around February, January, right? So anyway, there. So the fact that there is that also gave an idea that the Earth could not be at the center of everything. But the circular model was still a problem for all this. So, oh, by the way, elongations, right? When a planet is on the east or on the west, that's when you can find the elongations. You will do that in stellarium as well. It's pretty nice as you move the planet around the sun. And then the elongations actually are different for every planet, more for Mercury. And that's because the different elongations tell you that the orbit is not circular, but elliptical. All right, but Nicolaus Copernicus obviously didn't get to that point, all right, because he didn't have, first, enough observations, he didn't have a telescope, and well, the mathematics and the physics back in the 1500s was still not there yet, right? We're still getting there. So we still have quite some time from the 1500s to the 1700s, 1800s, when we actually were able to understand this. Now, remember that thanks to the observations, we can tell, or we can find the synodic and sidereal period. The synodic is the period with respect to the sun, and the sidereal with respect to the stars, all right? So the synodic period for Mercury is very small. For Venus is 584 days. But then for the Earth, obviously, is 365 days, right? But that's all respect to the sun. If you want to do it respect to the stars, then you get a very interesting value, and actually a value that makes sense because you are seeing it from a perspective where every planet is going around the sun, right? No respect to the sun. It's like in physics we call non-inertial observer. So you want to see an object moving and another object moving respect to that other object when you're at rest. So the stars are at rest, obviously, because they are very far distant, right? So you look at objects moving around the sun, but the sun is also moving. So in any case, Mercury, because it's closer to the sun, takes 88 days respect to the stars. But Venus takes 225 days. The Earth, 1 year, 365 days. Mars, more. As you go farther from the sun, the period is shorter because your velocity is also smaller. The period is related to that, right? So, oh, sorry, what I'm talking about. The period is larger because the velocity is smaller, right? Distance equals to speed times time. The same happens in circular motion, right? The angular displacement is equal to the angular velocity times time, period. If the period goes up, the velocity goes down. The farther you are, the lower the speed is, and the higher the period is. There you are, right? Physics. Again, some of those ideas were not that clear still 400, 500 years ago, right? So there it is. So we talk about inferior and superior conjunctions, right? Remember that in order to find those, we need to find the alignment between the Earth, the Sun, and in this case, Venus or Mercury for the inferior or superior conjunctions. Now, Tycho Brahe, he was the first astronomer to have his own observatory. He made a huge amount of observations, a lot. And he disproved ancient ideas about the heavens. But he had his own model. It wasn't even a heliocentric model. He had his own model, right, between 1546 and 1601, right? By using different observations, he disproved these ideas, right? He had the idea of parallax. He understood the idea of parallax, but his model still put the Earth at the center. So they were still fighting the idea that the Earth was not at the center of everything, right? And that's why the Tychian model, that's how they call it, right? It failed. In fact, you know what's the sad part? That he hired Johannes Kepler, the one who actually had the right idea of putting on, after Copernicus, right? Johannes Kepler, he realized that that wasn't really the way to go. So after Tycho Brahe passed away, he used Tycho Brahe observations because Tycho Brahe opposed that. So Kepler used his observations after he passed away to propose, first of all, the elliptical path for the planets. That was crucial to understand the following ideas. The fact that the planets don't go around the sun at the same speed, but they do cover similar or same areas at the same time, right? And then that there was a relationship between the period and the distance from the sun, right? There was a direct relationship there. So that's very important. And I always like to say or emphasize that thanks to Kepler is that we got some of the ideas from Newton. Newton did a lot, right? He invented calculus, the three laws of Newton, but the law of gravitation, his fourth law, some of that is built upon what Johannes Kepler introduced. Newton proved it mathematically. Kepler did it with the observations. He realized that the only way to understand the orbits of the planets, the retrograde motion of Mars, and every observation that Tycho Brahe did, right, was by using elliptical orbits. So what's the difference between an ellipse and a circle? You are seeing it there right now. An ellipse doesn't have a radius. It has a semi-major axis and a semi-minor axis. And it has a right triangle that you can build by using the two focal points, focus. And we can use the geometry and the math to prove that at least the second and the third law, which you can actually do by using nice physics and mathematics, conservation of energy and angular momentum. And we can prove that at equal times, you sweep equal areas. That's very important, right? I don't know how many of you have ever heard about Kepler's second law, right? Because he also has three laws, by the way. The first law is that the orbits are elliptical. The second one is that equal areas are swept at equal times. And the third law is that the period squared divided by the semi-major axis A cubed is a constant for every object that is orbiting a star. Nice, right? So again, the math is not necessarily, but the facts, the history of this is important, all right? Because now we're going into what? Well, first of all, let's introduce the idea of eccentricity. A circle has no eccentricity. A line has one. Between 0 and 1, that's where you have an ellipse. It's an elongated circle. The lower the eccentricity, the more circular-ish is an object. And guess what? Most of the planets in the solar system have very low eccentricities. So we can say that the Earth has an almost circular orbit. You know what's fantastic about that? That helps us realize that the reason we have the seasons is not because of the distance. Many people, when you ask them, why is it hotter on summer than on winter? Which is a question for the next chapter. They will say, oh, because the Earth is closer to the sun on the summer. That's not correct. The correct answer is because the tilt, right? I think everybody here knows that. But when they look at this, and that's the only thing that they get out of school, unfortunately, right? Oh yeah, the planets are going in ellipses. And then because of that, no, right? There's more in between. In fact, I would say that the orbit of the Earth around the sun has an eccentricity of even less than 0.5, that you see that. So it's very circular-ish, right? It's still an ellipse. There's still a semi-major axis, but the difference between the semi-major and semi-minor axis are not that much. And that's important. So this is what I was explaining about an ellipse, right? All right. Even though, well, there's an exaggerated ellipse in there, right? But there are some planets, maybe exoplanets, that may have that type of orbit. So it doesn't matter if the planet doesn't cover or doesn't travel too fast. The idea is the area. And now this actually allows us to explain that retrograde motion as well, and how far and close you are. The farther you are from the star, the slower you are. The closer you are, the faster you move. And that idea is used also in NASA for the elongation technique, which is, if you guys have seen the movie The Martian, you will remember that when the guys tried to go back to Mars because they knew they left an astronaut, right? So they wanted to go back and rescue him. They had the spaceship going towards the Earth. And then they do this, right? Because they use the gravitational potential energy as a slingshot. It's a slingshot method, sorry. And then they could do a jump. They gain momentum / energy. That is used. That's what happens when planets go closer to the sun. That's what we have seen with the stars orbiting black holes, by the way. The closer they are to the event, to the accretion disk, the faster they move. The farther they are, the slower they move, right? That is all conservation of angular momentum, right? But there you are. So I think what I want to get at is Galileo and Newton, guys. Because thanks to them is that we finally had the proper vision of the law of gravity and the solar system itself. Because it was Galileo who invented the telescope. It was Galileo who observed all this, the phases of the moon, the phases of Venus. So he knew that the Earth was not at the center, that the planets were orbiting the sun. That's what we see the phases, right? And then Newton was the one who elaborated his laws, and then the law of universe, the law of gravity, to realize that the planets were going in ellipses, that they fit the observations perfectly, and then therefore we see things like the phases of the moon. Or Galileo also discovered what? The Galilean moons. The Galilean moons that are orbiting another planet, Jupiter. So then he realized that that was like a mini solar system, right? So they made him retract the church, right? Ask him to, no, that's not correct. We're talking about what? Talking about like the 1600s. So it took a long time, since the Greeks to the 1600s. That's a lot of time. We're talking about probably more than a millennia with wrong ideas. You wonder why we cannot get to the moon yet. I mean, man-made missions, right? Because it took us a long time to catch up. So anyway, thanks to Newton and also Galileo, now we know and understand gravity, right? What do we know? That gravity acts like an instantaneous force. That a body will remain at rest unless I do this, unless I exert a force. That if the body is moving, it's accelerating. And what's the constant of proportion? The mass. F equals to ma. So more mass, more inertia. And then what else we know? For every action, there is an equal and opposite reaction. We use them locally every day. Thanks to them, we can launch rockets to the moon. We can place the ISS around the Earth. And then, combining those understandings, we get to the universal law of gravitation. And then we understand concepts such as the orbits, the escape speed, the orbital speed, right? It took us a long time to get there, but that's the main idea of this chapter, guys. Okay, so I want you guys to read the slides, to go through the textbook, and then I hope this video was helpful, all right? If you need it, I might put another video, but guys, watch the video that is on Canvas, all right? Have a good afternoon.